So today we're going to look at two-dimensional forces acting on an object. Does it rest on a horizontal surface? Combined with friction in what I call a will it move problem. And the goal is to determine if the applied forces are enough to overcome friction, and if it is, determine the resulting acceleration. The approximation I will be using here is that the coefficient of friction is just one value. I know if you're going to really dig down, there's a static and kinetic coefficient. If you understand the process, then that's what we need to do here. So my setup is going to be this. I'm going to have a 10 kilogram block at rest on a horizontal surface. Imagine it right here. I'm going to have a 100 Newton pulling force acting up and to the right at 30 degrees relative to the horizontal. And my coefficient of friction, I'm going to put it at a simple 0.1. And the first thing I want to figure out is how many forces are acting on this, and the really particular aspect of this problem that is different than, say, one-dimensional forces is that the assumption that the normal force value is equal and opposite to the weight of the object no longer holds true, because the normal force is much more than that. I'll get into that in a little detail here, but I'm not going to dig down super deep. So if I look at this, I know, unless I'm told otherwise, this is happening on the planet Earth. So I'm going to have a force vector downwards, which is my gravitational pull. And if we use that mass times the gravitational field strength, we get 98 newtons down. If we're using negative 9.8, you get 100 newtons down if we use negative 10. The really important aspect is, up until this point when I teach it, the first response is people want to do this and say, oh, my normal force is 98. If there were no other verticals acting and this object didn't move up or down, which there's nothing lifting it off the ground or pushing it through it, then the normal forces, the value would be equal to the weight. But we cannot assume that is the case, because we actually have another vertical force that is part of this force over here that is going to change the contact force between the surface and the block. But I do know I'm going to have a normal force because it is on a surface. So I can put Fn over here. And if this thing is going to move or attempt motion, friction is a force that always opposes the motion of an object. So I'm just going to put this guy back over here and say FF equals, and I do not know the value, but I'll figure it out relatively soon. I know I'm going to use the friction equation, which is the coefficient of friction multiplied by the normal force value. So I'm going to get that one set up. That's what I have. Those are the four forces in play right here. Next thing you want to do is look at the fact that this 100 Newton force is not only in the x direction or the y, it's a combination. So the only way you can add vectors mathematically, which is how we do this with Newton's laws, is you have to figure out how much of this vector is in the x direction, which is the fx component, and how much of this is acting in the y direction or vertical, and that's my fy component. So I'm going to break that down into its components, and if this drawing is big enough here, I can put my two little arrows right here, and if we go through the trig on this, this is going to be the hypotenuse times the cosine of 30 degrees here. My 30-degree angle is right there. And this is my Fy vector, my vertical force. That's going to be 100 times the sine of 30. Notice the direction of my vectors. This indicates the direction of the components. This is, quote, a quadrant 1 vector, which means it is a positive x and a positive y, where you're dragging it to the right and slightly lifting it up. So these are by default both going to have positive values on them. 100 times the sine of 30 is 50 newtons up. And 100 times the cosine of 30, I just got to refresh my memory on this one. .6 newtons. So technically, by doing this, I've just changed this and said, well, let's break this down and look at how much of this force vector is trying to, quote, lift it upwards or apply an upward force against gravitational pull, which is my Fy, and how much of this is trying to pull it to the right, which is the 86.6. So I'm going to restructure this and show you what this diagram looks like once I break those down. And we're back. I took those two component vectors and placed them on the diagram because that is how we resolve them. And this is essentially what goes on in both the horizontal and vertical direction in terms of the forces. We have an 86.6 over here. Once we figure out the frictional force, we'll be able to figure out if it moves, and then if it does, what the resulting acceleration is. The key to getting to the frictional force here is we have to figure out what the normal force value is. And I want you to think of the normal force as it's a force that one surface exerts when it presses against another one. So when surfaces are in contact, there are normal forces. This will produce a normal force on this one, and this will produce a normal force on this one. Now we're only looking at the normal force acting on the block, so it's 1/2 of that third law force pair here. But you can look at this and call this the strength of the surface, and the fact that the ground is going to resist and say, I'm made of asphalt or wood or something else, and I'm going to resist you just falling right through me. So it's a material strength characteristic, if you want to think of it that way. When I teach this, we never have the object break the surface, so that the normal force always has enough force to oppose any force trying to pass through it. So that means that the normal force will, quote, adjust itself so that there is no vertical motion. So when I solve for the normal force, I know that there's no acceleration or motion in the y direction, because there's nothing lifting this up off of the ground, and we have a surface that opposes its motion. So what that means is, now this means the sum of all the y forces have to equal 0, because that's going to mean the acceleration in the y direction equals 0 also. So all I want to do is some simple math here and look at the fact that if I take a look at this, I have a normal force, which is a y force. I have a 50 Newton force upwards due to the vector component of that 100. And I have the gravitational pull, which is 98 down. And notice everything is a vector sum. The direction is carried by the vector itself. Now this has to equal 0. So if we do some quick math here, we're going to see that the normal force is going to have to come out to be equal to 48 newtons in value, because we've, quote, lessened the pull of gravity, or we've counted the gravitational pull by 50 newtons, which means the normal force technically is only feeling, or the ground is only feeling 48 down. So that is the value of my normal force. This is a step that I tell my students I want to see, because I want to understand that they know what they're doing with this as far as the math. So now let's tackle friction. Okay, that guy right there. Frictional force is based on what is the, quote, roughness between the surfaces and what is the pressing force between those two surfaces. I kept the numbers fairly easy here, so 0.1 is going to be my coefficient of friction. And if it hasn't moved yet, I'm going to say it's my coefficient of static friction. And 48 newtons, which makes this a really, really, really low friction surface. My frictional force is 4.8 newtons opposing. So because the motion, or the pulling force attempting to move it is to the right, the friction will oppose with 4.8 to the left. Now I can look at this and take a look and say, well, step 5 is, are my applied forces magnitude-wise, are they greater than the frictional force? Well, Fx greater than Ff? Yes. I have 86.6. The magnitude of that is greater than 4.8, so it's going to move. So the last step is, what is the resulting acceleration? And the assumption I'm making is that the coefficient of friction does not change. We know it does. The acceleration in the x direction is the net force, or the sum of all the forces, in the x direction divided by the mass. I have 86.6 newtons plus a negative 4.8 divided by 10 kg. This thing's going to be honking. .18 meters per second squared to the right. And that's the general solution to a one-angled force with friction, determining if an object will move or not. Bye-bye. Time to finish my laundry. I can turn the machine back on. Joy.